Hello students, good day. I hope all of you are safe and doing good. In the last couple of weeks, we had discussed how memory management can be achieved in non-contiguous memory, and we discussed the concept of paging quite in some detail. This paging solves a problem of contiguous memory allocation, where we now can store a process onto the main memory in a non-contiguous fashion. However, there is still a problem which is even which exists even in this memory management, and that is what will happen if we have a memory size which is smaller than the size of a process. In the contiguous memory allocation, we use the concept of overlays, where we divide a process into multiple mutual exclusive partitions, so one is not dependent on the other. So if we can merge those concepts, the concept of paging and the concept of overlay, can we achieve the very same goal in non-contiguous memory allocation as well? So we will try to discuss these dimensions in virtual memory module. In today's class, we will discuss virtual memory, and then the concept of demand paging and page fault will be discussed in this regard. Uh, as we have seen in the concept of overlays, that it is possible for a process to be loaded in different partitions, the mutual exclusive partitions, where a complete program is not loaded onto the main memory at any point. So we were still able to achieve the successful completion or successful execution of a process, having its partitions on the main memory at any given time. So if we merge those two concepts, the concept of paging, where we divide a process into several pages and they are stored onto the main memory in a non-contiguous fashion, and the concept of overlays, where we only load portions of a process regarding its execution and need. And once some of those pages or some of the partitions of a process, they are no longer required, we can offload them from the main memory and can use that space for some other processes or maybe some other pages. So in today's class, we will look into this dimension. So will that be possible? We are already aware that in order to execute an instruction, it should be present in the main memory. However, at the same time, we know from the concept of overlays that if an instruction is not executing at a particular time, it can be offloaded from the main memory, or we can say that if an instruction associated with a process is not going to be executed in a while, it may not be loaded and still the execution of the process will not get affected. So if we have a process that has multiple subroutines, if we just do not load the subroutines related to some process, some subcomponents of that process, still it is possible to execute that particular process. This includes, for instance, error handling. So if a process doesn't end up in an error, it is possible that throughout the execution of your code, you may not required to even load that particular subroutine. So in the same manner, if we have several components associated with a process which may not be required for a journal execution of that process, it is possible that we may complete the execution of a process without even loading those components. So by this we can infer that if a process, for instance, has 100 pages, so it is possible that throughout its execution 20 pages of that process may not be required, and we can still complete the execution of that process if throughout the life cycle of that process execution we may not load them all together. So this raises the concept of uh, demand paging. So in paging, we used to load all the pages associated with the process onto the main memory. In demand paging, we only load the pages associated with the process that are demanded by the process. So this is a small difference between paging and the concept of demand paging. In paging, we are required to load everything associated with a process or all the pages of a process onto the main memory. In demand paging, we only load those we only load those pages on the main memory which are actually required by the process. There are several benefits when we have this limited loading of pages. And they include that if we are loading only 70% of the pages, then less time will be required for this transfer or this loading of pages onto the main memory. Also, now because we have more space on the main memory left after a process is being loaded, so it is possible that the very same space can be utilized by some other processes. So virtual memory provides us this separation of the logical memory from the physical memory. Now we are not required to load the complete process onto the main memory for its execution. So we use a small space onto our disk that we refer to as swap space, or we can utilize some external device for this swap space. And what we can do is that once we want our process to be loaded onto the main memory for its execution, instead of loading it directly onto the main memory, we move it to the swap space, and pages that are required by the process and they are demanded by the process, they are loaded at runtime. So the complete process is not loaded onto the main memory, rather it is moved to the swap space. On the swap space, the complete process is saved or it is placed, and once a particular page is required by a process, it is loaded at the time of its requirement. This whole process or this concept is termed as virtual memory, the concept of virtual memory. And this allows us to separate the views of the logical address space and the physical address space. Now we can have a process of 3 GB onto a main memory that is of 1 GB. So we have a process that requires 3 GB to be loaded onto the main memory. However, because now we have the concept of swap space as well as demand paging, so only those pages will be loaded onto the main memory which are required, and maybe at a particular time the requirement of that particular process may not exceed 1 GB. And once we no longer require the pages that are loaded onto the main memory, we can easily offload them and load the pages that are required by the process at that particular time. So this provides us a way through which we can have a main memory quite smaller compared to the size of the logical address space, and the programmer, they need not required to be worried about the size of the memory available in the system, or using overlays to write mutual exclusive partitions of the code. So there are various advantages of this virtual memory, and the discussion of this concept completes the big picture of this memory management unit. Here we have a conceptual model of this concept of virtual memory in practice, where we will see how a process that is larger than the physical memory can get executed. So you can see that over here we have the logical address space, and we have this smaller physical memory. So at the beginning, the complete process along with its pages are loaded onto the swap space, and from this swap space the required pages are moved to and from this main memory and swap space. So once a particular page is required by the process, it is taken out from the swap space and moved to this physical memory, the main memory. And once it is no longer required, or the space is to be used by some other process or some other page, then we can swap it back to this swap space. So in this way, the concept of virtual memory works when we have a process of whatever size is loaded onto the main memory in the presence of a swap space. The whole concept is the virtual memory concept. All right, so to summarize the concepts that we have acquired so far, processes have a continuous listing of instructions starting from the beginning of the process to its end, and on the other hand we have frames in the physical memory. So this memory management unit does this mapping of the logical address to this physical address, and we have seen that this non-contiguous mapping of pages onto frames is done through paging. And the concept of demand paging is where we only load the pages onto the frames when they are required by the process. When demand paging is implemented in a system, we only load the pages that are required by the process. This requires less input output, less memory is required for each process in journal, and we get faster response from the system because instead of loading the complete process onto the main memory, we only load those pages which are actually required at the beginning of the execution of that process, and we can have more processes onto this main memory of the same size if we load only the desired pages on the main memory. So when a particular page is required by a process, it checks the page table, and it checks whether the page is already loaded onto the main memory or not. This is done through a particular column in the page table. We call it the valid or invalid reference bit. If we have invalid reference, it means that the page is not mapped onto the main memory, so it is not loaded onto the main memory. So we have to go and fetch that page from the swap space and load it onto the main memory before we can continue with the execution of this instruction. If the reference bit is valid, then we can straight away fetch that instruction and start executing it. So when the page is not in the memory, we are required to raise a particular interrupt. By the way, this interrupt is termed as page fault. Page fault is an interrupt that is raised when the page is not present in the main memory, or the particular page search ends up with the invalid page reference. So we get to this page fault interrupt, and we get the page from the swap space and load it onto the main memory. Here we have the conceptual model of this demand paging. You can see that on the main memory we have two processes, A and B, and their pages are already present onto the swap space. So once a page is required by a process, they are swapped in from the swap space to the main memory, and once they are no longer required, they can swap out of the main memory to the swap space. There are a couple of bits that are used for this swapping in and swapping out. One bit, as we had discussed on the previous slide, is invalid reference bit. There is another bit that is the dirty bit that is used to ensure whether there is any modification while the page was there on the RAM. For example, if you have some data page onto the RAM, stored onto a frame of RAM, and there was some modification on that data page. So when you are swapping those pages out back to the swap space, you can write them explicitly. However, if there is no modification in a page that is swapping out to the swap space, then probably we can ignore that copying from the main memory to the swap space. So we can optimize the working of this demand paging through selective copying of pages from the main memory back to the swap space, only doing it when they are actually required. So there is also another concept of lazy swapper. This lazy swappers are used to support the concept of demand paging. They only load those particular pages from the swap space to the main memory when they are actually required. So in the concept of paging in journal, we can copy everything onto the swap space once the process is loaded onto the main memory to start its execution. So everything is there onto the swap space, and then we can load them whenever these are required. However, when we are dealing with the demand paging and the lazy swapper, we can only load the page when a request is generated by a process. Here we have the basic working of this demand paging. Once a process is scheduled to be executed, all the pages associated with this process are loaded onto the swap space instead of the main memory. And now we have a prediction algorithm that predicts the number of pages which are to be loaded onto the main memory, which are required to start the execution of this process. There are algorithms for this prediction. So once the initial pages are loaded onto the main memory, the process starts its execution. At every instruction, it checks from the page table whether the page is available in the main memory or not. For this, we have a valid invalid reference bit that is stored against this page number to frame number translation. If the bit is on, if this bit is valid, it means that the page is already in the main memory, which means that the process can continue with its execution without any further delay, just like in the usual circumstances of paging. However, if the page is not in the memory, if the bit is invalid, then it generates an interrupt that the page is not in the main memory. We call that interrupt as the page fault that the page is not present in the main memory. And then the operating system fetches that page from the swap space and loads it onto the main memory, and the process can restart its execution for that particular instruction. Here we have an example how the page table will look like with this valid invalid reference bit. So you can see that we have this translation in here, and these bits are set to valid or invalid. This valid means that the page is already in the main memory. We also call it memory resident pages, and this invalid means that the pages are not present in the main memory. When we have this bit set to invalid, we have a page fault. Here we have an example of a process having 8 pages. Over here we have the page table associated with this process. You can see that some of those pages are translated onto the frames, and their respective valid invalid reference bits are valid. And for some of the entries we do not have any frame number altogether, and we have their reference bit as invalid. So you can see that over here we have the main memory where all the valid pages are stored onto the main memory, while on the swap space we have the complete process along with its pages is stored onto this swap space. So here you can see the requirement of the demand paging and what will happen when we have a reference to this entry where we have invalid as the reference bit. So if we are trying to execute an instruction that resides in this page which is valid, so this is exactly the same as we had in the paging. So for 0 page number we will fetch frame number 4, and while once we are here we can extract that particular instruction and we can execute it. However, if we have an instruction that we are going to execute onto a page that has invalid as the reference bit, so over here this process will generate an interrupt, that is the page table, meaning that the page is not in the memory. So first of all, the operating system will fetch that desired page from the swap space and put it onto this main memory, and then update this page table and enter the relevant frame number over here, and then restart that particular instruction to continue the execution of that process. Once we have a reference to a page that is not present in the main memory, it generates an interrupt, that is the page fault. The page is not present in the main memory. In order to respond to that interrupt, the operating system fetches the page from the swap space, find a free frame on the main memory and load that page from the swap space to the main memory. To achieve this, it copies that particular page from the swap space, then it finds a free frame from the main memory, then it copies that page from the swap space to the main memory, and once this is done, then it updates that page table. It updates the reference bit of that particular entry. It modifies the frame number against that particular page number, and then it informs that particular process to restart the instruction that caused the page fault, so that the process may continue with its regular execution. Please be reminded that this process doesn't require any intervention from the programmer. So programmers can write down their code without even knowing that these pages will be loaded onto the main memory or not. The operating system will handle everything on its own. So unlike overlays, this demand paging concept doesn't require any modification of the actual process. So programmers can write down their set of instructions in a usual contiguous fashion, and everything is handled from the loading to the actual execution is now dependent on the operating system. Here we have a diagram showing different steps that are involved in the handling of a page fault. So this is our logical address space. Over here we have the page table associated with the process. This is our main memory. Over here we have our swap space, and this is our operating system. So once the process tries to execute an instruction that resides on a page that is not memory resident, so once the reference to that page is initiated by this process, it checks that page table whether there is a mapping to some frame number or not. So once it checks that this reference bit is invalid, it generates a trap. This is known as the page fault. It tells the operating system that the mapping of page to frame is not present in this page table. So you are required to fetch that page from the swap space and bring it to the main memory. So in response to that page fault, the operating system goes to the swap space, fetches that page from the swap space and copies it onto the main memory. However, before copying it to the main memory, it requires some free frame, and it searches the whole main memory in order to find a free frame where this particular page can be loaded. So we have some algorithms to find those free frames, but for now we can assume that some free frame can easily be found by the operating system. Once it gets that free frame, it copies that onto this free frame and write down this mapping over here and updates this reference bit as well, and informs the process to restart its instruction. So once all of this thing is updated, the process can restart the execution of that particular instruction, and in the meanwhile, as this bit is valid now, the process can easily get this translation and get that particular frame on the main memory. There is an interesting aspect of demand paging where we do not load any page altogether on the main memory when we start the execution of a process. So once we decide to execute a process, we do not load any page onto the main memory. Rather, we just put all the pages onto the swap space. And once the process starts its execution, the very first instruction generates a page fault, and then the operating system fetches the first page and loads it onto the main memory. So in this way, only those pages that are required by the processes are loaded onto the main memory. This aspect is usually known as pure demand paging. So a process is only loaded onto the main memory when it is purely demanded by the process, and we do not predict the initial pages to be loaded for a particular process. Another aspect of demand paging is when one instruction can cause multiple page faults. This can happen when we are executing an instruction that has different components in different pages. So if this happens, we may have access to multiple pages in order to execute a single instruction. However, this may not be the case in usual fashion, because we have locality of reference where in journal we write down our code in a way that the data parts are closely related to each other. Alright students, so that is all for today. In today's lecture we discussed virtual memory, and in this regard we discussed the concepts of demand paging as well as page fault. I hope you remember that when we are dealing with the page fault, the operating system fetches a page from the swap space and puts it onto the main memory. However, we expected at that time that there is always a free frame available in the main memory. However, this may not be the case always. So what will happen if we do not have a free frame present in the main memory? So in such cases, we may find a particular page that we can swap out of the main memory. So we will discuss all of those related concepts in the coming lecture. So I will stop it here for today, and I wish you a safe stay. Thank you.